Dear students, in this video, we will study electrostatics, which means study of charges at rest. So, in this video, we will study about frictional electricity, charging by induction, properties of charges, Coulomb's law, superposition principle, electrostatic forces, and electric field and lines of forces. So let us begin with frictional electricity. Now, frictional electricity is the electricity produced by rubbing two bodies and transfer of electrons from one body to another. Now, let us look at this activity. Here, a glass rod is rubbed with a silk cloth, and you can see that the glass rod has become positively charged and the silk cloth has become negatively charged. Another activity, an ebonite rod rubbed with a flannel cloth. Now, the flannel cloth becomes positively charged and the rod becomes negatively charged. Now, the electrons in glass are loosely bound in it than electrons in the silk. So when glass and silk are rubbed together, the comparatively loosely bound electrons from glass get transferred to silk. As a result, glass becomes positively charged and the silk becomes negatively charged. Now, the body which has lower work function. See, the body with lower work function loses electrons and becomes positively charged, and the body with higher work function gains electrons and becomes negatively charged. So it's very easy to understand. See, when two bodies are rubbed, energy is produced due to friction. Now the electrons in the valence band, they absorb the energy, and if the work function is low, then they easily leave their parent nucleus and get free and jump onto the other body. Now, what is work function? It is the minimum energy required by electrons to leave their parent atom. So, work function is something like ionization energy. So let us talk about properties of charges. And here, first property, quantization of charges. Now, charges are integral multiple of charge on an electron. And charge on an electron is 1.6 into 10 raised to the power minus 19 Coulomb. So, any charge can be expressed as plus minus NE, where N is 1, 2, 3 or any integer. Now you can see that NE is charge on one electron and N is any number. So any charge is integral multiple of charge on electron. It's very easy to understand. You see, if you have any two bodies and for charging, say electron is jumping from this body to the other one, second electron jumping to the other one. So clearly the body which loses electrons becomes positively charged and the one which gains negatively charged. So they will gain equal and opposite charges, and charge will be equal to charge on two electrons. So it is not possible to transfer, like here two electrons are being transferred. It is not possible to transfer 1.5 electron or 1/4 of electron because electron is indivisible. So therefore any charge is quantized and charge on electron is the minimum possible charge or basic charge. So the next one is, okay, one interesting example. Now let's see how many electrons are present in 1 Coulomb of charge, which is SI unit of charge. So in 1 Coulomb, we will have 1 upon 1.6 into 10 raised to the power minus 19 electrons. So this number is 6.25 into 10 raised to the power 18 electrons. So this is a huge amount of charge. So that is why we use smaller multiples of Coulomb like millicoulomb, microcoulomb or nanocoulomb. So the next property is conservation of charge. Now, the algebraic sum of positive and negative charges in an isolated system will remain constant. Means the total charge present on any body will remain constant. Charges can move from one place to another. Like basically it is the electrons which move from one place to another. So redistribution of charges is possible, but the total charge on a system will always remain constant. So see, if the electron is moving from this side to this side, this end will become deficient, will become positive. The side which gains electrons will become will have excess of electrons, so will become negative, and so on. So the next one is charge is a scalar quantity, that you already know. Charges are additive in nature, that you already know. Like charges repel and unlike or opposite charges attract. All these properties are known to you. So let us learn another method of charging, that is charging by induction. Now, when a charged body is brought closer to an uncharged body, some charges are induced in the uncharged body due to redistribution of electrons. So let's see this example. Here we have two metallic spheres placed in contact with each other, and then they are mounted on insulated stands. Now, when a charged rod is brought closer to them, this positively charged rod attracts electrons. So electrons get attracted from this side to this side. So obviously this side becomes excess, the nearer end becomes negatively charged because of excess of electrons, and the farther end has deficiency of electrons, so it becomes positively charged. And now if the two spheres are separated, then this one will become negatively charged and the other one will become positively charged. So both the spheres are charged with opposite and equal charges just by bringing a positively charged rod closer to it and not in contact. The next example is, these charges are actually called induced charges. As you can see, induced charges. So induced charges positive here and the negative on the other one. Now let us see another example. Okay, so in this case you can see a positively charged rod is brought closer to a metallic sphere, which again is mounted on a non-conducting stand, and this again will attract electrons towards it, and electrons are free charge carriers in metal, so electrons can move. So this end becomes negative and this end becomes positive. Now in the second diagram, what happens is that this positive end is connected to ground. You can see it is grounded. So electrons will flow into the sphere through this conducting wire and they will neutralize these positive charges. So positive charges are finished. Now the next possibility is, now the connecting wire has been removed, and here this positively charged rod is held closer to this one, this sphere. So negative charge is held at this place. Now this rod is removed, and now the negative charge gets equally distributed all over the metallic sphere. So this sphere is charged by a negative charge just by bringing a charged rod closer to it. If we want to charge it by positive charge, then we have to bring a negatively charged rod closer to it. So this kind of charging is called charging by induction, and the charges produced are called induced charges. The next topic is Coulomb's law, that is force between 2-point charges. So here the statement, okay, let's try to understand. See, we have 2-point charges Q1 and Q2 placed near each other, distance r apart. Now the force between them is directly proportional to the product of the charges. So larger are the charges, greater will be the force acting between them. Also, the force is inversely proportional to square of the distance between the two charges. So it follows inverse square law, and combining these two together, we get this relation F is equal to K Q1 Q2 upon R square, and this K is a constant of proportionality. Now for direction of this force, the force is always directed along the line joining the two charges. Now what is this constant K? This constant K is equal to 1 upon 4 pi epsilon naught, where this epsilon naught is the permittivity of free space. Now permittivity is a property of a medium, and it represents the ease with which electric field lines can pass through a medium. Now another physical constant called dielectric constant, or relative permittivity, or specific inductive capacity of a medium. So here this is equal to okay, you can see that this relative permittivity of a medium is equal to the permittivity of medium divided by permittivity of free space. It is also called dielectric constant K. So now the relation for electric field, relation for this electrostatic force becomes 1 upon 4 pi epsilon naught into Q1 Q2 upon R square, and in vacuum K is equal to R. K is equal to 1, or this epsilon naught R is equal to 1. Now for any other medium, see, the K is the minimum value. For all other media, this value of K is more than 1. See, in any other medium, F is equal to 1 upon 4 pi epsilon naught into epsilon R, which is permittivity of the medium. So we can write epsilon R, or we can also write K, dielectric constant. So that is the modification of relation in other media. Now the value of this permittivity. Now in free space, the value is 8.85 into 10 raised to the power minus 12 Coulomb square, Newton raised to the power minus 1, meter raised to the power minus 2. Now the value of this constant 1 upon 4 pi epsilon naught is equal to 9 into 10 raised to the power minus 9 into 10 raised to the power 9 Newton meter square Coulomb raised to the power minus 2. So Coulomb's law in vector form. So we need to represent the forces as vectors. If we have two like charges, two positive charges placed distance r apart, then the forces act along the line joining the two charges and they will be repulsive forces because like charges repel. We can take pair of negative charges. Now they will also repel. So in vacuum for Q1, Q2 greater than 0. See, Q1, Q2 greater than 0, that means for like charges. Now look at this situation. Here Q1 is repelled by Q2. So the force is along this direction. The force on Q1 is F12. And direction of this force is from Q2 to Q1. So direction of this force is acting along this direction. So F12 is acting along R21. So let's see its relation now. So F12 is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square R12, and F21 is just the opposite. And now relation for two unlike charges. Now here one is positive, one is negative, and unlike charges attract, as you know. Unlike charges attract. So Q1 is attracted by Q2. So now the force is acting along R12. See, Q1 is pulled by Q2 along this direction, and this is direction of R12. So in vacuum for Q1, Q2 less than 0, that means for opposite charges. See, if one is positive, one is negative, the product will be negative. That means we can say that we have unlike charges. So now see the relation. The forces F12 and F21 are equal and opposite in all cases. Now another definition of dielectric constant. So let's see dielectric constant once again. Okay. The dielectric constant is ratio of forces acting between any two charges between when placed in vacuum and when placed in medium. So if two charges are placed in vacuum and the force between them is Fv, and then the same charges are placed in a medium and force between them is Fm, then this ratio Fv upon Fm is equal to dielectric constant K or relative permittivity. So this is one way of defining dielectric constant. So now let us see one numerical based on Coulomb's law. If we have two charges, 2 microcoulomb and 5 microcoulomb placed at 20 centimeter in air. See, calculate the force acting between them. So first let's see the given values. Q1 is 2 microcoulomb and micro means 10 raised to the power minus 6. So and Q2 is minus 5 microcoulomb. or 5 into 10 to the power minus 6. Distance between them is 20 centimeter or 0.2 meter. So all the physical quantities have to be taken in SI unit. So we have converted them in SI unit. Now, since they are opposite charges, they will attract. So attractive force between them is given by this relation 1 upon 4 pi epsilon naught Q1 Q2 upon R square. Now the value of this 1 upon 4 epsilon naught is 9 into 10 to the power 9. Putting the values of Q1 and Q2 and R, we get this relation. And now the next relation is calculating. You have to do calculation and the force comes out to be 2.25 and it is an attractive force. Now, when it is immersed in water, system as such is immersed in water, then we have this relation that K is equal to Fv upon Fm or Fw water. Then clearly, force in water Fw will be equal to Fv upon K. And the value of K is given to you, so we can easily calculate it. Now the force in medium or in water is Fv upon 80, that is 2.81 into 10 raised to the power minus 2 Newton. The SI unit of force is Newton, that you already know. Now let us do variation of forces with distance from charges. Now according to this relation, you see that force is inversely proportional to R square. So when R is 0, F, okay, see, when R is 0, F is infinity. So the graph will not touch this screen, the graph will not touch anywhere on this axis. And here also, when R is infinite, then only F is 0. So here also it is not going to touch the line. The range of electrostatic force is infinite. Clearly, F becomes 0 only when R is infinite. Now another very important graph which is often asked in examination. Now, for like charges, the graph between F and 1 upon R square. See the graph between F and 1 upon R square. So F is proportional to Q1, Q2. Now Q1, Q2 positive means like charges, and this is the graph for like charges, and Q1, Q2 negative means for unlike charges. So for unlike charges, the force is negative. Now, if this is F, you can see that for 1 upon R square, F is equal to K Q1 Q2 into 1 upon R square. Now, since 1 upon R square and force, these two are x's, so clearly F is proportional to Q1 Q2. That means we are going to have a straight line graph. I hope you understand this graph. This is a board problem only. Now, superposition principle. Now, what if we have large number of charges placed in close vicinity? You can see that this charge Q is placed near charge Q1, Q2 and Q3. So, force on this charge Q1 is this charge Q. It experiences force due to charge Q1 along this F1. See, both the charges are positive. So, Q will be repelled and the force will be along the line joining the two charges. Similarly, this plus Q is also repelled by charge Q2 along this direction and the force is F2, and Q3 is negative charge, so plus Q is attracted by it towards plus q is attracted by charge minus q3, experiencing force F3. So three forces F1, F2, F3 are acting simultaneously at this charge plus q. So the resultant force on it will be vector sum of these three forces, and which is equal to this resultant force F. So now we have this relation, net force is equal to F1 plus F2 plus F3. So here comes a statement. Net force acting on a charge due to presence of multiple charges in its vicinity is given by the vector sum of the forces acting on it due to each one of them. So this principle is called superposition principle. Now let us do a numerical problem based on this superposition principle only. Now the problem is, find force acting on 2 microcoulomb placed midway between 1 microcoulomb and 5 microcoulomb, placed 20 centimeter apart. So you can see that we have two charges, 1 microcoulomb here and 5 microcoulomb here, and this 2 microcoulomb is placed just midway between them. So now charge Q1 will repel charge Q2. So the force F1 acts between them. So force F1 between plus Q1 and plus Q is okay, lesser than force F2. Just see how. This Q2 will repel Q, and the force acting is F2. Now F1 and F2 are in opposite directions, but you can see that Q1 into Q is lesser than Q and Q2. Therefore, F2 is greater than F1. F2 is greater than F1. So the forces are acting in opposite directions, and the resultant force, the magnitude of resultant force will be F2 minus F1. Now on calculation and using Coulomb's law, the result comes out to be, see, 7.2 Newton. You can do the calculations and check it. So in this way we can use superposition principle. Electric field. Now any charge will, if we have any charge, maybe a positive or a negative charge, it will influence all the charges around it, whether positive or negative. So this region around this charge is called its electric field. Okay. Now the electric field extends up to infinity, but practically it is limited to a certain distance. Now strength of this electric field. So electric field strength or electric field intensity. So let us define it. Electric field strength at a point in an electric field is the electrostatic force per unit positive charge acting on a vanishingly small positive test charge placed at that point. So if we have, say, some positive charge, and because of this I want to find out electric field at this point. So what we do is we place a very small positive test charge. This test charge is extremely small, vanishingly small. Then the force per unit charge at this force per unit charge will be called electric field at this point. This is property of this point. See the same diagram, you can see. Now if it is a positive charge, you can see that. Now this is positive charge. It's electric, this will push this positive test charge away from it. So direction of force is away from it, and direction of electric field is also away from it, because by definition this electric field and electric force will be along the same direction. So electric field is directed away from a positive charge. For a negative charge, it is going to be just the opposite. Now you can see that. See, this is negative charge. It will attract the test charge towards it. So force is towards it and electric field is along the direction of the force. So electric field is also towards the negative charge. So direction of electric field is very clear. It is directed away from positive charge and directed towards negative charge. Now, why do we take test charge as extremely small? See, the test charge is vanishingly small. If it is large, then it will modify and affect the existing electric field. So we assume that this test charge Q naught is approaching 0. It is not 0, but it is very close to 0. It has to be small, and by convention we take it as a positive charge only. So you can see that from here, direction of electric field and direction of force have to be same, and electric field is equal to F upon Q naught. And you know the relation of force, so we can get this relation for electric field now. You see, this is relation for electric field in vector form. 1 upon 4 pi epsilon naught Q upon R square along this unit vector R. Now since Q naught is taken positive, the direction of electric field is along the direction of the electrostatic force, as I have already told you. Now electric field is a vector quantity whose magnitude and direction are uniquely defined at every point in the field. Now SI unit of this electric field is Newton per Coulomb. And later on, we will get to know that SI unit is also equal to volt per meter. So SI unit of electric field is Newton per Coulomb, force per unit charge, and later on it is going to be volt per meter also. We'll study that in another unit now. Now electric field due to a point charge. We have a point charge plus Q, and then test charge placed at distance R. You see, this is test charge placed here. So now the force acting on the charge, test charge, is equal to 1 upon 4 pi epsilon naught Q naught upon R square. So force is given and electric field strength is F upon Q naught. Therefore, we will divide this relation by Q naught, and then you can see that in vector form the electric field is 1 upon 4 pi epsilon naught Q upon R cube R vector, or this is also equal to 1 upon 4 pi epsilon naught Q upon R square and unit vector R. So when you put unit vector, this denominator is R square, but when you put vector R, then denominator becomes R cube. And just to remind you, see, unit vector is equal to vector r upon its magnitude r. So that is why we get this r cube term in the denominator. Look at this graph, variation. So this is variation of electric field. So when r is infinite, you can see, when r is infinite, electric field is 0. When r is 0, electric field is infinite. So the graphs are very important here. The electric field due to a point charge has spherical symmetry. Okay. Properties of electric field lines or lines of forces. So let us take their properties. And before that, let us know what are electric field lines or lines of forces. Now, in any electric field, if a test charge is placed, then the path followed by the test charge is termed as electric field line. You can see that. An electric line of force is an imaginary straight or curved path along which a unit positive charge is supposed to move when free to do so in an electric field. So electric line, these are, we cannot really see them, but these are just imaginary lines. So electric lines of forces do not physically exist, but they represent the real situation, the properties. Number 1, the electric field lines of forces start from positive charge and terminate on a negative charge. Tangent to an electric field line at any point gives the direction of electric field at that point. See here. Here. Okay. We have electric field. This is electric field line. And at this particular point, the tangent is along the direction of electric field. So this yellow electric field line, as you can see, its tangent drawn at this point shows direction of electric field this. If the point is here, the direction of electric field will be this. If point is elsewhere, the direction of electric field is this. Some more properties. Okay, electric field lines of forces due to uniform electric field are parallel. So in uniform electric field, the lines of forces are parallel, as you can see here. Here we have two plates, one is positively charged, another one is negatively charged. This is negative and this is positive. Now the electric field lines between them are from positive plate to negative plate, and the plates are parallel. Therefore electric field is uniform and we get parallel lines. Now two electric lines of forces can never cross each other. If they do so, then at the point of intersection there will be two tangents, and it means that there are two values of electric field at that point, which is not possible. As you can see here at this point, two electric field lines shown with yellow color, they are crossing. So we are going to have two tangents, electric field E1 and electric field E2. Now at one point, we cannot have two different directions of electric field. So therefore it is just not possible to have, for two electric field lines to cross at any point. So we can say that. Further, electric field lines being a vector, there can be only one resultant field at the given point, which can be represented by one tangent only at at a given point. This is a very important point to note. Okay. For isolated charges, now see, if you have an isolated charge like this one, Q is plus Q, then electric field lines are directed radially outwards from it. Electric field lines are directed radially outwards from a positive charge. And you can see that, yeah. Now another thing is that if the charge is more, the electric field lines will be denser. If charge is less, electric field lines will be rarer. So at the places of stronger electric field, the lines will be closer, and at the places of weaker electric field, the lines will be rarer, farther away from each other. So here, electric lines of forces are closer, crowded, where the electric field is stronger, and lines spread out where the electric field is weaker. Okay. Another interesting thing is electric field lines are always normal to a charged body. You can see that I have shown you a charged body and electric fields are shown normal to this surface. If the body has irregular shape, then also electric field lines are always normal to the surface of a charged body. And this we have already discussed. Okay. For a positive charge, electric field lines are directed away from it, radially outwards, and for negative charge, when Q is less than 0, then electric field lines are directed towards the charge, radially inwards. You can see representation here for isolated positive and negative charge. Now let us see what happens when two charges are placed near each other. You can see the example here. When electric field lines due to pair of equal and unlike charges, like you can see here, we have shown you one positive and one negative charge. Now see, electric field lines start from this positive charge and they are directed away from it. As soon as it reaches near the negative charge starts attracting it and it reaches here. See, if I place a test charge here, then the test charge will be repelled by positive charge and it is being repelled. But as soon as it reaches closer to negative charge, the negative charge attracts this test charge. And you know that test charge is a positive charge plus Q naught. If the test charge is placed exactly between them, then the test charge will be repelled by the positive charge and attracted by the negative charge. So that is how these electric field lines are formed. You can see. Okay, another point. See, electric lines of forces contract lengthwise to represent attraction between two unlike charges. You can see the contraction of electric field lines. It shows that these positive and negative charges are attracting. Let us see the situation for two like charges here. Now just try to understand here also. If I place a test charge here, then it will be repelled by this positive charge, and as soon as it reaches here, the repulsion due to the other positive charge also occurs and it is bent away from it. Similarly, if I place a test charge here, then it will be repelled and finally repelled away from it. And we can say that due to repulsion between like charges, you can see here, electric lines of forces exert lateral or sideways pressure to represent repulsion between two like charges. So we'll have similar diagram for negative charges also. Only thing is that the direction of electric field will be reversed. Now electric field lines do not pass through a conductor. That's a very important situation here. You see, electric field lines here, this is a positively charged plate. They start from positive charge, they reach the solid surface or solid or hollow conductor, but there are no electric fields between the conductor, inside the conductor. And then on this side here, see, negative plate. Now electric field lines are reaching it starting from here, but there is no field inside it. Now see, due to the positively charged plate, negative charges are induced here. This end becomes negative. Negative charges are induced here. So the electric field lines are starting from positive charge and terminating at negative charge. Now due to this negative plate, positive charges are induced here. Positive charges, and the electric field lines are starting at positive charge and terminating at negative plate. But there are no electric field lines inside the conductor. This is called electrostatic shielding. Now, if any instrument which we need to save from or safeguard from electric field, it must be kept inside a hollow conducting box. So electric lines of forces can pass through an insulator. I mean, they cannot pass through a conductor, but they can pass through an inductor. Thank you.